So, consider a generalized ordinal potential game as we defined in the strategic form, and let P, function P from S to reals, be such a generalized ordinal potential. Among many, perhaps. Of course, among many, we can at least always change the function by adding the constant to all the function, but not only. In the case of generalized ordinal potential, not all. Now, let G prime be the same game when instead of the utilities, all the players have the same utility defined by the function P. Then the Nash equilibria of the new game are a subset of the Nash equilibria of the original game. So if something is a Nash equilibrium of the new game, G prime, then it's a Nash equilibrium of the original game. In particular, if there is at least one, I'm talking about pure only, Nash equilibrium of the new game, then definitely there is at least one Nash equilibrium of the original. Now, if P is not only generalized ordinal potential, but an ordinal potential, if we have a stronger requirement, which holds, then actually the sets of Nash equilibria are equal. And the proof is simple. So the first proofs here will be simple, just as a warm-up. So it's nice that the theory helps us to warm up first. Consider a generalized ordinal potential. Now, something is a Nash equilibrium in the new game. What does it mean by the definition? It means that for every player and for every possible TI, it's at least as good to play for player I, it's at least as good to play her strategy, her role in the equilibrium in S, and it is to play TI, when the rest keep playing S minus I. And we're talking about G prime, so we're talking about as good in the terms of the new potential of the new utility function, which is the potential by definition of G prime. Now, being at least S means that the potential in the strategy profile S is not smaller. It's simply another way to write greater recall. Is not smaller than the potential when player I divide and the rest keep playing as well. And therefore, and here we use the assumption that P is a generalized ordinal potential. The utilities in Si S minus I are not smaller than the utilities in Ti S minus I. That's basically the contrapositive of the definition of a generalized ordinal potential. So, because I remind you that the definition says that if the utilities are larger, then that's also larger. Now, if the utilities are not larger, excuse me, if the utilities are larger, then the potential function is larger. If the utilities are smaller, potential function is smaller, simply by changing the order. The contrapositive means that if the potential function is not small, then the utilities were not smaller. And so that is from here to here, that's the contrapositive. Now, please pay no attention that if P was a potential, not only a generalized ordinal potential, but a potential, a full-fledged potential, then we would have an equivalence here. And from here to here, we move simply because not smaller is at least as large as. So, assuming that S is a Nash equilibrium in the new game G prime, we have arrived at a situation when S is at least plane SI is at least as good for player I when the other play S minus I, as playing any TI in SI. So we have got to the situation that S is a Nash equilibrium in the original game, and thereby we have proven the Nash equilibria in the new game are included in the Nash equilibria in the original game, because we have done it for any Nash equilibrium S in G prime. And as I said, if we assume that P is an ordinal potential, then we would have had equivalence here. So the other direction, the other implication would also hold. So then we would have the Nash equilibria of the new game, when we replace the utilities by the potential, are the same as the Nash equilibria of the original. So it's not even necessary to be a potential game. It's enough to be a generalized ordinal potential game. Quite a weak requirement. And already the Nash equilibria of this new game are in the Nash equilibria of the original game. In particular, we're going to see now about an important implication about existence. And if you know that there is an ordinal potential, again, we don't have to be a potential or a weighted potential, just an ordinal potential, a little weak ordinal, not a little small requirement, a weak requirement, ordinal potential. We already are allowed to look at the Nash equilibria of this new game when you just have potential functions for every player. And the first corollary is that a generalized ordinal potential game where there exists a generalized ordinal potential which admits a maximum, which attains a maximum, I mean, such a game has a Nash equilibrium. And the proof is trivial. Let me just change the admitting to attaining. I think that's a better word. Now the proof is quite simple, because such a maximum is an equilibrium in the new game, because the utilities, they are potential, so the potential, they cannot, if it's a maximum, then in particular no lateral deviation can improve it. Actually, no deviation can improve it. We are not talking about strong equilibria and such things, if you know what that is. So we are talking about only lateral deviation, but actually we have something strong. It's a maximum, so definitely no deviation can improve it. So it's an equilibrium of the game G prime. And therefore, there exists also an equilibrium of the original game, because we know that the equilibria of G prime are included in the equilibrium of the original game. Yeah. Now, corollaries from the corollary. So when do we know that there exists an ordinal, that there exists a generalized ordinal potential which attains its maximum? For example, if the game is finite, so if the starter sets are all finite, so in particular the set S, the Cartesian product of all strategy sets, is finite. Or from basic topology, you may know that if the generalized ordinal potential game strategy sets are compact according to some topology. For example, in the case of the strategies being real sets, being compact means that they are closed and bounded. And that's not very important for this course, but we need that. We will study that at some point. If you don't know actually what it is, please look it up. If you need, please ask me. So a game with compact strategy set and a continuous generalized ordinal potential function also has an equilibrium because a continuous function on a compact set, and of course a product of compact set is always compact, not of course, but it's always compact. Such a function always attains its maximum. But mostly we are going to talk about finite games. Okay. By the way, please notice we can jump also. We can also look at this mountainous landscape, and we can be at a mountain peak which is not the highest, not the maximum, and still no unilateral deviation can change it. So I don't only speak about the case that we have a maximum. It's not that it's necessary, but it's enough. It's enough for an equilibrium. And another topic which is we're going to study, and that also has some relationship with physical intuition. That's paths. Path in the space of the strategy profile. A path is the sequence of strategy profile. Such that maybe finite, maybe infinite. Such that for any t, for any time, t is the index of the sequence, and for any, there is the player and a strategy I for the si prime for the player different from what the player did in the previous step from s t minus 1 I from what the player I did in time t minus I. In the element t minus I, time is just a way we can look at the 16 sequence holding. Such that what the player does at time t is basically, what the path has at time t is that player changing, because s prime I is different from what the player did, and the rest of the players are doing exactly what they did at time t minus 1. So exactly one player, there exists exactly one player at each time that changes her action. Not more, not less. Now, we call that S0. The S0 is the initial point of the path. And if the path is finite, so if there is a last profile, then the last, of course, it's the only one, then that last profile in the sequence we call the terminal point. Start from the initial point to the terminal point if top. You can look at finite sequences. Even on a finite game, we can have infinite sequences, for example. You can just circle, positive circle at some point, but we can have. Well, if you go to somewhere where it was, it will not like necessarily circle and then continue whatever it used to do before, but it can definitely, it will cross itself if it's an infinite sequence on a finite in a finite game, but it can be. And of course there can be a sequence of any finite length on an infinite game also. So the options are any option. Now just an example, what is a path? So ABC was the original strategy profile. So 3 players, one playing A, another playing one playing B, another the third one playing C. Then player 2 changes from B to B prime. So exactly one player changes, the rest keep doing what they used to do. Then player 1 changes from A to A prime. The rest keep doing what they used to do. So 2 keeps doing B prime, 3 keeps doing C. So exactly one player changes with respect to the previous step, to the previous node on the path, or point on the path. Let's call it a point. Now, not a path. You may stop the video and look why that's not a path. And no, that's not a path because, so look, we first start with ABC, then exactly one player changes. B goes to B prime. I assume B prime is different from B. And here we have two player changing simultaneously, so they can not change simultaneously in a path. Both the first player changes from A to A prime, and the second player changes from B prime back to B. That's not a path. Okay, that's an important definition. Exactly one player changes. Okay, we're going to all this. It's important for us to look at this one player changes. So when we talk about potential, we looked at one player, exactly one player change in the strategy. At the equilibria also. That's an important motive. It's an important thing to talk about. It's not the only thing we can talk about. We can talk about what if 5 players change in the same time. But it's definitely natural to, let's say, at least start with exactly one player change. So see that we are talking about similar things. And by the way, you see how important that is, how related the logic here is to the logic of Nash equilibrium. So I definitely advocate studying that topic at least to some depth on the basic course of EM theory. I definitely advocate that. Another notion, which is finite improvement path. Now, a path is a sequence. Okay, that was it before. Just at any point t, there is some player that changes. That's a test t. Basically, is made of that player I going to do some si prime, which is different from what the player used to do in t minus 1. And at oh, yeah, typo. The rest keep doing what they used to do in the previous point, not in the beginning, in t minus 1, like here. Oi. Of course, a typo. Let me see. Finite improvement path. I need to fix it. Yeah. Okay. So now to change to s2 minus 1. Finish compiling. No, that was the definition already. No. Okay, now that's t minus 1, s at t minus 1. No. Now a path is called an improvement path. Similar. Please, let's continue. A path is called an improvement path. With respect to a game, if the for any t, the utility of the unique deviator is strictly increasing. So when I is the unique player change strategy between st and st plus 1, utility of player I is strictly increasing. Please take note, we don't require anything about the utility of the player. Definitely, if the game is, let's say, the identical utility game, it will also strictly increase, but maybe it will decrease. We saw these examples already. So we only require that the utility of the unique deviator that has to strictly increase. for the path to be called an improvement path. Now, the game is set to have the finite improvement property, or FIP, if every improvement path is finite. So, as defined, an improvement path can be infinite, but if every improvement path is finite, you cannot define a path which has this improvement property and is infinite. If every improvement path is finite, then the game is set to have the finite improvement property, FIP. It's all very much related to one another. So there are many definitions, but they are very logically consistent. So what happens to one player changes, whether we can trace it by a potential, what about the path of exactly one player changing all the time at any point, of course not necessarily the same player, and so on. There is definitely a logic about what we are studying here, what we are defining here, and therefore many theorems are, if not intuitive, let's say at least not surprising. So, and the intuition of this finite improvement path is every myopic improvement process. Myopic improvement means that the player who changes, exactly that player, at least that player has to improve. What happens? Exactly that time that she changes, and such a process has to stop. It cannot go forever. That's the intuition of a finite improvement path. And there is an important lemma. If a game is finite, then having a generalized ordinal potential, so it's quite a weak requirement, remember, is equivalent to having the finite improvement property. So FIP is not a finite improvement path, but a finite improvement property. That's important to remember, even if I sometimes will call it finite improvement path. A path can be finite, but FIP is finite improvement property. So you cannot, like in this illustration by Escher, you cannot constantly improve and constantly and be circling. That's the intuition. Okay, let's prove. So first, one direction. So if the game has the generalized ordinal potential, then to have an improvement path, by the definition of potential and the improvement path, the potential will strictly increase, because by the definition of an improvement path, the unique deviated utility always increases. It can be that first player 1 deviates, then again player 1, then player 5, then player 3, then again player 1, then player 4, whatever. But the unique deviator has the utility increase. And by the definition of potential, that means that the potential will increase. It's enough that we have a generalized ordinal potential. It's strictly increasing. Now, it cannot increase indefinitely because the game is finite, as we assume. So it has to terminate, and therefore this path terminates, so we have the finite improvement property. Now, the other direction is that if we have the finite improvement property, then we have the generalized ordinal potential. Now, that's not hard, it just may look a bit longer, but let's wrap our head around it, not into that. So, not bang our head onto that, but actually wrap it around. It's much better to understand things than worry about them, right? Okay, after this few more moments, let's go back. So, conversely, assume that the game has the finite improvement property. And we want to define a generalized ordinal potential. Now we define a binary relation of the set of strategies. Basically, we define which two ordered strategy profiles are related in a certain way. We define that S, profile S, is strictly smaller than profile T. in the sense that we define now. It's strictly smaller on this new set in the sense that we define now. If they are not exactly the same profiles, and there exists a finite improvement from initial such that its initial point is t and its terminal point is f. So we can go from t to f to s. Excuse me. It does not actually matter. Yeah. From S to T to T to F, let's define it, it will be enough. So just a step from T to S. Now, since we assume the final improvement property, there cannot be that there is a finite improvement path in the other direction too, because then it would cycle, and the finite improvement path cannot cycle. Excuse me. The finite improvement I'm confusing, my apologies. The finite improvement path cannot cycle because that would contradict the finite improvement property, which is assumed. So there can be no okay, so my apologies for the confusion. I know I fix all this, it should be clean. So look, first s is smaller than t if s is not equal to t and there is a finite improvement path from s to t. So the s is the initial point of that path and t is the terminal point. Now, since we cannot have a finite improvement path from t to s2 because then we would have a circle, which means that the finite improvement property would be contradicted, and since we assume it holds, it means we cannot have a circle. Therefore, it cannot be that we have s smaller than t and t smaller than f. That's what it means. So that's what we have from this finite improvement property. We don't get such contradictions. And the concatenation, we always may concatenate finite improvement paths, implies transitivity of the relation we have defined. So we define the relation which is not reflexive because nobody is smaller than itself by definition. And we don't, if one is smaller, then the opposite cannot hold, at most one hold, one of the relations hold, and this time. Now, what does it mean to prove that the game has an ordinal potential? It means to prove that for any subset there exists a function from the set of the profiles in this subset of S. Excuse me. There should exist a function from S, from all S to real numbers, such that if X is greater than Y, in the sense that there is a finite improvement path from Y to X, then also P of X should be strictly greater than P of Y. That means to say that P is a general ordinal potential representing that, which fits to that game. Now, how do we prove there is such a P? We say that, okay, a subset S of S, now it's a subset, maybe S, maybe it's a strict subset, Z, is represented if there exists some P, such that for any two items of that, X being greater than 1, in the sense we define, implies that P on X is greater than P on 1. Now, we want to say that the proof that all S is represented in that sense. And that will be enough. It means that there exists such a P. Now, take a maximal, so the represented subset of S. A maximal means that there is no strictly including a subset, which is also represented. And assume by contradiction that there exists an element outside of that. If they prove that it is not the case, then it means that the only maximal such that is S. Now, why there is an element outside of it? By the way, there can be no case there exists no Z because any singleton is represented trivially. So there exists at least one maximal such that, and therefore the argument is not vacuous. So it makes sense. Okay, so then we want to show that this leads to a contradiction. The assumption that there is someone outside of this maximal representative. Now, and why? If that X is greater than Z for any Z in this Z, then we can extend the P, which is defined in Z, to Z, which has also X, by taking the maximum of P over Z and adding 1. Then it will be greater than anything on Z, and since X is greater than any over Z in Z, then the larger set Z united with X, with the singleton including S, will also be represented, contradictory to the assumption that Z is a maximal represented subset. Analogously, if X is smaller than over Z in Z, then we just extend P to Z when we add X to that set by looking at the minimum value of P on Z. It's finite, so don't worry. We assume making element it's finite, so we can look at the minimum value, and subtracting 1, so P will be the smallest, strictly smaller than any P on Z, and since X is strictly smaller than any Z in Z, then P will be also representing this larger set, so Z united with X, and that contradicts an assumption that Z is a maximally represented set. And the other option, the only other option, so that it's not, X is not larger than everyone and it's not smaller than everyone. It can be that the only other option is that look at a maximum value of P on those elements of Z which are smaller than X, and look at the minimum value on those elements of Z which are larger than that. And to be on the good side, we just need to prove that we can extend P such that it will be exactly strictly smaller than the minimum of P on all the elements which are larger than this, and strictly larger than all the elements which are smaller than that. And it's possible by taking the, for example, the arithmetic average of A and B. Now, A is strictly smaller than B, that's important. If there is nobody which is, for example, strictly smaller than that, there is no requirement of that side, so we just can take A to be anything which is smaller than B. So if there is nobody, they can just take anything, because the requirement is only when they have some path, some finite improvement path. But if there is someone, then A is smaller than B, because those who are in A are those Z who are smaller than X. Those who are in B are the values of P on those Z who are larger than S. By transitivity, which we have, every value in B is larger than every value in A. And therefore, since it's infinite, the minus over B is also strictly larger. The minus over this set, the second set, which is B by definition, is strictly larger than the maximum on this set, which is A. So the minimum over this set, that every element is strictly larger than the element of this set, is also larger than the maximum of the smaller set. So in any case, we can extend this Z, and therefore it contradicts the maximally represented subset, which is not all S, so it has to be all S. So therefore S can be maximally represented, and that basically means that the game has a generalized ordinal potential. So we have proven that a finite game has a generalized ordinal potential, with the weakest definition we started with, if and only if this game has a finite improvement property. So not like in the picture by Escher. Okay. Corollary. A corollary. Now, for any player, if for any player and any profile and any strategy for this player other than what the player plays in that profile as, for any possible deviation, the utility after the deviation will not be the same as it used to be. Larger or smaller does not matter, but it will not be the same. So no deviation by no player from no profile will leave her utility the same. Every time someone deviates, her utility changes. And if the game possesses a finite improvement property, then the game has an ordinal potential. And the proof is simple. So the finite improvement property implies a generalized ordinal potential, as we've just proven. Now, the requirement, what it basically says that it cannot be just a generalized, it actually has to be ordinal, stricter than generalized. It's stronger than generalized. Why? Okay, so let's see. The condition implies intuitively that generalized requires some equality at some point. Despite the player changes, what she does, that unique deviator does not change her utility. That's basically the difference between the generalized ordinal potential and an ordinal potential. And here it cannot be that the utility does not change by our assumption here. So that's the formula. So the idea what we know is that the finite improvement property implies we have a generalized ordinal potential. And that means that if the utility strictly grows, then the potential strictly grows. Or in other words, if the utility is larger, when I move from one to another thing, then the potential also is larger. Now, the contrapositive would be if the potential is not larger, then the utility is not larger. And our assumption that the utility cannot be the same implies that the utility has to be strictly smaller. If the potential is strictly smaller, the utility has to be strictly smaller. And that's the other direction, which, in addition to the assumption that if the utility is smaller, the potential is always smaller, says that basically the game has an ordinal potential, not just a generalized ordinal. Okay, now the next question